Hi all, in this class we can see what is the capacity of a channel of infinite bandwidth. So in previous class we studied what is Shannon's Hartley theorem. In that we found what is the capacity of a band limited Gaussian channel. So in that we studied that C is equal to B log of 1 plus S by N bits per second, where C is the channel capacity, B is the bandwidth and S by N is the signal to noise ratio. In addition to that, we also studied that what is the bandwidth signal to noise ratio trade-off curve. So in that we studied that for the same channel capacity, we can reduce the bandwidth if we are increasing the signal to noise ratio. So in that example, we studied that if you are if you are reducing our bandwidth up to 25%, then we need to increase our signal to noise ratio about 60%. So that is the bandwidth signal to noise ratio trade-off. So also we can make some conclusions that if we are increasing the bandwidth, we can increase the information rate or the channel capacity, because C is linearly proportional to B. As well as if we are increasing the signal to noise ratio, we can increase the information rate or the channel capacity while still preventing errors in the errors due to noise, because this signal to noise ratio and C, the relation is C related as logarithmically proportional to the signal to noise ratio. But what is the condition if there is no noise? There is no noise means signal to noise ratio becomes infinity. That means S by N, that N becomes 0, so S by N become infinite. So for there is no noise, you will get the channel capacity or the information rate as infinite with irrespective of bandwidth. So if there is no noise, we have infinite capacity is possible irrespective of bandwidth. Then what is the condition if we are increasing B to infinity, or if we are taking B as infinite? So if B tends to infinity, the channel capacity doesn't become infinite. Why? Because with an increase in bandwidth, the noise power also increases. We know that the noise power spectral density is eta by 2. Then the noise power N is related as eta B. So if we are increasing the bandwidth, at the same time the noise power is also increased. So if the noise power increased, the channel capacity doesn't become infinite. So we can say that there is a limit if we are increasing if we are making the bandwidth as infinite. So we can see what is that capacity of a channel of infinite bandwidth. So we already said that according to Shannon's Hartley law, our C is equal to B log of 1 plus S by N bits per second. And if when B is increased, channel capacity of C also increases, since the maximum rate of transmission is equal to C. This is enhanced any large value as we wish if we are increasing the bandwidth. But channel capacity doesn't become infinite when the bandwidth is made infinite. So this is saying that if we are increasing the bandwidth, the channel capacity also increases. But if we can't make the channel capacity as infinite if we are making the bandwidth as infinite. So we can see what is the limit or what is the maximum limit of this channel capacity if we are making this B as infinite. So this is because we already said that when B increases, the noise power N, which is dependent on B, also increases, thereby reducing signal to noise ratio. Thus the product of B and log of 1 plus S by N will increases only up to a certain value and becomes constant with increasing B. So now we can find the capacity of channel at infinite bandwidth. It can be represented as C infinity. So we know what is C. C is equal to B log of 1 plus S by N, where N is eta B. So for this equation we can multiply and divided term, that is S by divided term with S by eta. So you will get it as C is equal to S by eta into eta by S. That means S by eta by S by eta becomes S by eta into S eta by S, B log of 1 plus S by eta B. In this S by eta we can take as one term, and in this eta B by S we are considering together. So you will get S by eta into eta B by S log of 1 plus S by eta B. So we know one thing, that means A into log B is log of B raised to A. So we can write this as S by eta into log of 1 plus s by eta b raised to eta b by s. Then we can replace s by eta b as x. So you will get it as c is equal to s by eta log of 1 plus x all raised to 1 by x. Next we can take the limit as b tends to infinity. So if b tends to infinity, this s by eta b becomes 0. That means x by infinity is 0. So that means x tends to 0. So when b tends to infinity, x tends to 0. So we can write the equation as limit b tends to infinity or x tends to 0. C is equal to limit b tends to infinity, x tends to 0, s by eta log of 1 plus x all raised to 1 by x. So this expression as b tends to infinity, we can write c as c infinity, which is equal to s by eta log of limit x tends to 0, 1 plus x all raised to 1 by x. So this limit x tends to 0, 1 plus x all raised to 1 by x is nothing but e itself. So we can write c infinity as s by eta log of e to the base 2 bits per second. So this is the we can say that this is the maximum capacity if we are increase the bandwidth, if we are taking the bandwidth as infinite. So the c infinity is equal to limit b tends to infinity, c is equal to s by eta log e to the base 2. So it is nothing but 1.44 s by eta bits per second. So this is the maximum information transmission rate possible for a system of given power but no bandwidth limitation. So if you are not considering any bandwidth limitation, then this is the maximum possible information we can transmit, or the maximum capacity, channel capacity is equal to 1.44 s by eta. So the power spectral density we can also write as eta is equal to k into t equivalent. So this is the, we can say that this is the maximum capacity capacity possible for a system of given power but no bandwidth limitation. So this is the channel capacity of infinite bandwidth.